I'm grateful to be able to speak at this meeting. I can't claim to be working on celestial holography, but all the more I feel an obligation to try to connect what I do with the main focus of this program. And so I want to get to what was originally the title of my talk, Holograms in Asymptotically Flat Space. But I felt that this was going to be more productive if I back off a little bit and sort of explain where I'm coming from and where that research program originates. And so that's why there are these other two parts. First, I don't expect necessarily everybody here to be familiar with that end of the story. So let's get started. Part A is gravity as an oracle. So this is a way of thinking that has kind of congealed in my mind over the last few years, especially, but maybe over the last 10 years already up to a point. And it's the fact that gravity is unlike any other force. I mean, that's sort of trivially true. It's at the heart of most scientific revolutions since antiquity. And it's special in that it couples to everything. But one thing that maybe is not as appreciated is that general relativity, our classical theory of gravity, seems to know in some sense about quantum mechanics. And there's, of course, no parallel in any other part of physics to this statement. And I feel like we urgently need to learn more about what sense exactly that is and how to harness that power. And let me start with what in hindsight seems to me like the beginning of that story, though maybe at the time it wasn't viewed that way. When Hawking discovered black hole radiation, the way that this was sort of presented as shocking is mostly from the point of view of, well, classically black holes can't emit anything, and now when we treat them a little bit quantumly, suddenly they do. Isn't that shocking? I think that's actually not the shocking part. Classically, you couldn't heat up anybody, any object to non-zero temperature. It would take infinite energy, and so nothing would radiate anyway. So maybe it shouldn't be so shocking that black holes radiate when you include quantum effects and not otherwise. What I think in hindsight is the real surprise is that Hawking was able to compute how they radiate. That's really outrageous. That to be able to compute for an object that you don't have in your lab and you have no idea what its microscopic structure is, that it radiates thermally with a specific temperature, which then allows you to use the first law of thermodynamics to deduce its entropy. That is not supposed to happen. In the 19th century, we knew about, or somebody knew about entropy by having stuff in their lab and measuring how much energy it takes to heat it up by a degree. And then with quantum mechanics, we can compute, given enough information about the microscopic structure of an object, we can compute in how many ways it can wiggle or how many quantum states it can have. For black holes, we had neither, and we still don't for most black holes. And yet we have great confidence that the entropy of a black hole is given by its surface area in units of 4 GH bar. So in that sense, classical gravity, with just a little bit of quantum dressing, doing quantum field theory on a Schwarzschild background, seems to tell you about its own quantum states. Now, I'm going to jump back and forth multiple decades a few times. I'm going to jump almost to the present just to illustrate how this power has sort of, at least in my perception, sort of exploded and become even more overwhelming. Normally, of course, when we say that the entropy is roughly the number of quantum states, that's a hand-waving statement. It really measures roughly the number of typical quantum states in an ensemble, ones that are not very unlikely, compared to the average quantum state. And so e to the entropy is not really an integer. Whoops. Sorry, let me just see if this still works. Yeah, it does. But of course, if you have an enormous amount of ground state degeneracy, then it should be an integer at 0 temperature. And I want to remind everyone, especially people who were not around in the 90s, what an unbelievable triumph it was when string theory, using all the gadgets that had just been invented, dualities, brains, the kitchen sink, in the 90s was able to explain and derive this exact integer number of states for certain supersymmetric black holes. So not just e to the area over 4, which would be impressive enough, but the actual exact number. So a recent development, which I found very impressive, is essentially a rederivation of this from what seem like more universal arguments that don't require us to use these particular ingredients, but basically just apply the gravitational path integral in a very careful way. This is work not only of Eliezu, my colleague Luca Eliezu here, Murthy and Toriachi, but it really builds on work of many other people. And the way, I can only sketch it briefly because it's not the main topic of my paper, but the way that it comes together is, to me, very beautiful, because you use the gravitational path integral to basically sum over infinitely many geometries. Each term is some horrible transcendental thing, and you arrange them in the right way, and it becomes the famous Hardy-Ramanujan-Rademacher expansion that was developed in analytic number theory to count partitions of integers and other related objects which are manifestly an integer, and therefore it sort of resums to an integer. I thought that was definitely way beyond what I expected we would ever get out of a calculation like that from just using the gravitational path integral. I want to jump back a few decades again. Gravity not only knows about its own quantum states, it's pretty clear that once you buy into these ideas that led to black hole entropy in the first place in the 70s, like you want there to be a second law of thermodynamics that's preserved by the area of a black hole growing when you throw a teacup inside the black hole. Well, the area of a black hole grows by an amount that is supposed to depend on crude things like the energy and size of the teacup, and yet in order for it to grow enough to save the second law, it would seem to have to know something about the microscopic structure of the teacup and how many states it can have. And when you push this far enough, you get entropy bounds that initially were maybe thought to apply to regions or objects that could be converted into a black hole. But in fact, they also apply to the universe and really any space-time, any surface in any space-time you like. Roughly the amount of entropy that passes through what's called a light sheet of a surface. So you pick your surface, you find null geodesics that emanate orthogonally from it and are not expanding, and then you look at the matter that's captured by this light sheet, and that turns out to always be, the entropy of that turns out to be less than the area you started from. Apologies. Today, so going forward again 15 years, we understand this covariant entropy bound to be a consequence of the quantum focusing conjecture. So really, there's a set of ever stronger statements. Bekenstein conjectured the generalized second law. That's a consequence of the covariant entropy bound, which in turn turns out to be a consequence of a statement which is actually rather primitive. It's just saying, let's take the classical focusing statement that light rays are focused, not anti-focused, by classical matter, by matter that has non-negative energy density. And let's see if we can correct this for the fact that in the real world, in quantum field theory and relativistic field theories, matter can, in fact, have negative energy density. The null energy condition does not hold. The area theorem, for example, does not hold because of this, but it can be corrected to the second law of thermodynamics, generalized second law of thermodynamics, which is really a quantum area theorem. We try to do the same thing for the focusing theorem of classical GR. That gave us a conjecture, and the conjecture implies as a special case this bound. But more importantly, it had an immediate, highly non-trivial implication for quantum field theory without gravity. And that, to me, was really a kind of turning point. The quantum focusing conjecture, which I don't have time to explain the technical details of, and neither really of this explanation, of this consequence of it here, but it leads in one or two lines of trivial algebra to something called the quantum null energy condition. There is no lower bound, of course, on the energy density of matter in quantum field theory. There were various integrated statements known, like the average null energy condition. But it turns out there is a lower bound in terms of this quantum information theoretic quantity, it's a kind of second derivative of the von Neumann entropy as you cross the point that you're interested in and include more information. The reason that I thought this was a turning point is that it's, not just like, oh, the matter entropy can't be bigger than the area, and then you try it, and you fall very short of actually saturating it if you try this in this room. It doesn't seem very tight. It seems like conceptually interesting, this sort of area scaling, holographic scaling. But here we could prove, so first we proved in free field theory, this is a statement just about quantum field theory, so you can try to prove it. And we were able to prove it in like 20-some pages of algebra in free field theory, and then Tom Faulkner and his collaborators proved it in interacting theories. And this actually built on a lot of incredibly important, difficult technical work on modular flows and so on, Tom Hartman's work. And it was, to me, a watershed moment because, in the end, it turned out to be true. And you can, in fact, prove it, but it was really hard. It hadn't even been noticed, even though it's a fairly simple statement to write down. And so it shows, I think it really illustrates the power of general relativity as a discovery tool.
Can I ask you a question?
Yes.
So can you go back to the last slide?
Yeah, of course.
So in the right-hand side, you have these two derivatives of the entanglement entropy. So for a string safety, is there a bound, or can this two derivative also go to minus infinity?
Yeah, it could. I mean, it could become arbitrarily negative. I mean, I wouldn't discuss minus infinity.
We can make sense of this bound that if something is greater or equal to minus infinity, like.
No, it's not a bound that is. So it's a state-dependent bound, is what this means. So I need to know what the quantum state is, but it doesn't. You don't. I mean, if you replace the right-hand side with minus infinity, I would agree that it's trivial. I would not recommend doing that. Not that I'm aware of. I mean, we were. It's related to. There's various derivatives of. I mean, there's the relative entropy, which has to be positive, and then it also has to be monotonic. And this is like an inequality on the second derivative of the relative entropy, and it's not clear that that's universal. I mean, it's probably not. Like in a condensed matter system, it would not be true.
The left-hand side is true at the left-hand side is stress energy at a point.
It's the stress energy tensor contracted twice with the same null vector at a point.
And what's the region taken?
So what I want you, okay, I was hoping not to get into the details of this statement. So, but basically, the simplest example would be where you start with like a half space, and your point sits on the edge of that half space, and then you deform the edge outward a little bit along the same null direction that this vector k points into, and you ask how does the von Neumann entropy of the half space change when you start including that little bit of a new region. And you want to use transverse sizes that are longer than your effective field theory cutoff, for example, to make sense of these things. Good. All right. Another example of what gravity knows is it apparently knows that quantum information is both lost and preserved. So I want to discuss both of these claims that you can get out of semi-classical gravity. One is, of course, Hawking's famous calculation, which is incredibly robust. I mean, it just relies on the horizon of an old black hole being basically empty space. And it will tell you that the von Neumann entropy of the density operator of the Hawking radiation just grows monotonically, and then when the black hole is done evaporating, it plateaus, of course, because nothing else happens. And this created a huge hullabaloo, as you can imagine. You can also ask, so this is interesting because the answer depends on how you ask the question. You can also ask general relativity to compute the entropy of the Hawking radiation for you directly. In other words, you ask what the entropy is, not what the density operator is, that you would then feed into a formula for entropy. And that's effectively what my colleague Geoff Penington did in 2019 And parallel to his paper, there was one by Almeri and colleagues. And the way that you can get general relativity to just zoom in on that one question is called the quantum extremal surface prescription, but you can think of it as a shortcut for a procedure where you get general relativity to compute all the integer Renyi entropies by using the replica trick. It's a pretty straightforward generalization of what Gibbons and Hawking did to compute the thermal entropy in the 70s. You specify boundary conditions, just replicate them n times, and then let gravity fill in the bulk and use some saddle point approximation. And then you have to analytically continue that to n equals 1 to get the von Neumann entropy. This method for computing entropies was, of course, invented by Ryu Takayanagi at the classical level in 2006, but this connection with the replica trick was only understood in 2013. In any case, that is what these people did. And just to make sure, this did not work out. All right, here we go. Just to make sure that the Lukowitz-Maldacena argument still goes through, there were separate papers, again, both by Penington and by Almeri et al., that checked this at the level of computing the separate Renyi entropies and making sure that everything still works. But in any case, what they found, as I'm sure you already know, is that gravity tells you, when you ask the question that way, that the entropy goes up and then down again. It yields the page curve. That's precisely how the entropy should behave if the black hole returns quantum information. So that's an example, I think, along with Luca Eliesio and collaborators' work in recent years, very recent years, where I feel like it's sort of an exponential growth of how well we're exploiting this ability of gravity to give us answers to really interesting questions about quantum gravity. You may have noticed that there was a bit of a contradiction between Hawking's result and Penington's, which is odd given that they used essentially the same technique in the broad sense that it's semi-classical gravity or gravitational path integral in some approximation. And I've suggested, I don't know if this is true, this is one of the things that we don't, I think, understand well enough, that this might be the case because gravity computes some kind of average. There's one setting when we're dealing with JT gravity on the one hand, where there's some evidence that this is related to the kind of average that you do in the SYK model, and there are fairly precise statements along those lines by Sarchenker and Stanford and others. But in any case, so more generally, we don't know what gravity is averaging over, but if it were averaging over theories with maybe slightly different coupling constants, perhaps over different smearing over time in some way, it's not clear what the average is, but then it's at least consistent that the average entropy is not the same thing as the entropy of the average state. For example, if you have lots of unitary theories, in each one of them, the entropy will follow the page curve, so the average does. But if you average all these pure out states, you get an ensemble, which will have some non-zero entropy. But really, this gets us already to a point where it becomes a little frustrating that we have all these amazing results, and it's a bit of a dark art. Like, oh, how do you ask the question? How do you approach the oracle? Which, waiting for the smoke to come out. We should be able to turn this into an industry. And it seems almost irresponsible not to try really hard to do that, because who knows what else it can tell us. I want to give this one more example just because it will be central to the rest of my talk when I move on to parts B and C. When we ask the question, okay, in ADS-CFT, one sort of solid example of a complete quantum gravity theory for a certain class of spacetimes, we can ask the question, and we did ask this question starting in around 2012, what if I have access only to some sub-region of the boundary, labeled B here? So I have access to a reduced state of the CFT, reduced to that sub-region. What can I still describe, or what can I recover about the bulk? And it turns out that classical gravity can answer this question to a very good approximation. The answer was given earlier by Ryu and Takayanagi, but it was pointed out only by Wall that it's the answer to this question. And the answer is you look for the minimal surface that's homologous to this boundary region. It likes to sort of hang into the bulk like this because of the hyperbolic geometry. So the reconstructible region is what's in between. It's the homology region. And because of the history of this proposal, the Ryu-Takeyanagi proposal, it's called the entanglement wedge. It should really be called the hologram. Now this prescription was refined over the years. Again, initially it was just a classical area of prescription, in fact, only for time-symmetric settings. It was quickly generalized to time-dependent settings by Veronica Hubene and Mukund Rangamani and again Takeyanagi. And then Faulkner, Lukowitz, and Maldacena were the first to include a quantum correction. They said, oh, let's not just take the area of the minimal surface to be the thing that computes the entropy of the CFT region that it's homologous to. As a correction, also please include the von Neumann entropy of the matter in the homology region in the bulk. Okay. Well, that's actually something we can give a name to. It's called the generalized entropy of the homology region. And Engelhardt and Wall in 2014 said, well, really, to make this hang together, we should just extremize that as one thing. Not first extremize the area and then add some entropy to it. Just take that one object and extremize it. And that has the advantage that it has a potential of being valid to all orders in GH bar. And in hindsight, that step, minor as though it may seem, was absolutely essential for the discovery of the page curve. Because in that case, the homology region includes an island whose boundary is in a place where you have to sort of balance the classical expansion against an equally strong quantum term. So the quantum correction is not small at all. Now you might think that that was the end of that story, but in fact it was not. Sorry, these pictures looked a lot more high-res on my computer screen at the time. But this Minecraft object here is my former student, Chris Akers. And he and Penington pointed out in just very recently, just 5 years ago, that in fact, even the quantum extremal surface prescription can be wrong at leading order in certain weird quantum states that people who know more about quantum information theory than I do are aware of, but that had rarely been considered in examples in sort of ADS-CFT. And I don't have time to go into the detail, but they fixed the problem. And I found the fix amazing just because it taught us that gravity cares about, to me, totally obscure quantum information or quantum communication protocols, something called single-shot quantum state merging, which I swear I had never heard of. And what's relevant here is that to determine what the entanglement wedge is, you basically have to ask whether intermediate homology surfaces have enough area to perform quantum state merging across them. I don't know if that helps. And then you look for the largest region where that's possible, roughly speaking, and that's something called the max entanglement wedge. And there is a sort of dual object to that called the min entanglement wedge, which corresponds to some perverse communication task where you set yourself really low goals. You just want to have an epsilonic probability of not failing. And the key point here being that there end up being two separate sort of notions of entanglement wedge, which coincide only in certain states, which for most of us are the only states we have to worry about, which are in some sense actually quite special. They're called compressible states. One thing that's important for later is that these max and min entanglement wedges still obey entanglement wedge complementarity in the sense that the max entanglement wedge of some ADS boundary region, the min entanglement wedge of some ADS boundary region B is the complement in the bulk of the max entanglement wedge of the boundary complement. I hope that wasn't too much in one go, but maybe the formulas are easier to read. All right. I already said this, entanglement wedges should really be called holograms, and I will use the two terms exchangeably. We learned already from Lukowitz and Maldacena in 2013 that their construction actually has nothing to do with ADS-CFT. It's just that I think mainly this lesson wasn't absorbed because it's very hard to find non-trivial minimal surfaces anchored to infinity of other kinds of spacetimes. But really, it should be possible to generalize this notion of entanglement wedges or holograms beyond ADS. There's no reason why not. It's entirely a semi-classical construction based on really not much more than a generalization of some path integral that Gibbons and Hawking did in 1977. And so I want to describe my efforts to do just that. This was jointly with Geoff Penington. Before I summarize the prescription for these wedges, let me just, I've never really told you exactly what I mean by a wedge. So a wedge is supposed to be a set in spacetime that's equal to its double space-like complement. So for example, if I started with some partial Cauchy slice here, this green disk, and I took its space-like complement, meaning everything in the spacetime that's not in its past or future, I would get this wedge labeled A prime here, and then taking the space-like complement again, I would get this full diamond region there. Okay, yeah. So that's a wedge A. The disk itself was not a wedge. This is a useful object to discuss just because, once you have this diamond-like thing, it doesn't really matter which Cauchy slice of it you want to talk about. It contains the same information either way.
Same thing as what we call causal diamond, or is
well, people have used the word, I've used the word causal diamond to mean you take a world line and you take the intersection of the past and future of its future and past endpoints, and that's not exactly the same thing. That's roughly because light rays going in one direction, light rays going in the other direction focus differently, and so it's not. Yeah, it would not. You'd have to double complement that to get a wedge. Yeah. So the union of wedges is always defined with an implicit double complement. So for example, for this blue and turquoise wedge here, in both of these examples, the purple thing is the wedge union. Okay. Now, how did we define holograms in spacetimes other than ADS? The first and sort of most important thing that you don't have anymore is the ADS boundary. So you can think of the ADS prescription as a map, right, where you start with a certain boundary region, and then the map defines a corresponding bulk region, and you call that the entanglement wedge. The key question here was, what is the input to the map when I don't have ADS boundary regions anymore? I may not have any conformal infinity at all. And so we decided to take as input any bulk wedge, A. And then the next question, at least in hindsight, that one should ask is, what is the analog of the homology condition in ADS? So in ADS, we say the entanglement wedge should have the same conformal boundary, should have sort of the boundary region I started with as its conformal boundary, right? That's what it means. And it turns out that it's useful once you go to bulk input wedges to break that statement up into, it should be no more and no less. Like break the equal sign into a no more and no less. Make two statements out of it. The no less is a statement that, sorry, this should be a lowercase e here, by the way. Sorry for the notational difference. That the entanglement wedge of a bulk input region should contain the bulk input region. Okay, so that's criterion number one. And criterion number two, which Geoff and I didn't quite get right, and so that's something I've recently been working on in unpublished work with my student Sami Kaya. Criterion number two is actually is a little more subtle. Geoff and I were focused mostly on bulk input regions that still live in asymptotically ADS, where our prescription works pretty well. But once you go to asymptotically flat space, and this is why this is an appropriate venue, you realize that it does not actually work correctly. And so we had to think a little harder about how to define this. So we can think of the second condition, right, as saying that the entanglement wedge of an ADS boundary region must not have an asymptotic boundary that overlaps at all with the complement of that input boundary region, right? It must not overlap with it at all. And in that language, our task becomes to identify a bulk region, which I'm going to call the fundamental complement A tilde, with which our entanglement wedge of a bulk input region must not overlap. Okay? So the reason I call it the fundamental complement is really that it plays that role of like the other side of the boundary in ADS, where we know, in the ADS case, we know fundamentally these degrees of freedom are completely independent. It's a CFT, there's no gravity in it, so we know for sure that those are independent degrees of freedom. In the bulk, we always have gravity messing up our understanding, and so sometimes there's some known localities and degrees of freedom are not independent, but this region A tilde, I claim, will really be independent. And so I'll tell you in some detail, in much more detail than I'll tell you about the rest of the prescription for bulk entanglement wedges, because it's important here. I'll tell you how to construct this fundamental bulk complement of a given bulk wedge A. Okay? So there's two steps. It's not going to be that involved. And I think I'm going to use the stick now because this thing is too wiggly. These are three examples, one in asymptotically flat space, one in asymptotically ADS, and one in de Sitter on the right. All of them are meant to be in sort of generic spacetimes. That's why there are these gaps here. Generic meaning that these are not the vacuum spacetimes. I've thrown in a little bit of matter. Otherwise, you might not see some features that are kind of useful to know. So the conformal shadow of the, so this is an input wedge here. I've taken this to be a Rindler wedge. And its conformal shadow is computed by taking its past and its future and asking where that intersects the conformal boundary. And I've had to double the space-like infinity here to show this to you as a Rindler wedge, but this is really one point. So that part of conformal infinity that is causally connected to my input wedge is what I call the conformal shadow. Now you go and take the complement of that, sorry, next slide, on scry. So same pictures, nothing changed. But now I want you to focus on what wasn't in the conformal shadow. That's the green part. Well, for that I first have to tell you how to construct this. Right. So the next step is I find the rest of conformal infinity. That's not a wedge, but I can take its double complement, and that's going to be our A tilde. Okay. Now, when you do this, so in Minkowski space, you know, as in ADS, in the vacuum, these two wedges would touch, but it's a fact of it's related to the Gauss-Wall theorem. That Wall theorem, not Wall, that in generic settings they move apart a little bit.
What do these things look like if you kind of look? I mean, like the Rindler wedge is very kind of misleading compared to like it's just a one generator of scry. I try to show the other transverse directions, like how do these intersect?
Yeah. So this. In the vacuum case, this would really be two exact Rindler wedges touching each other. And then in the generic case, they open up a little bit, and both of these wedges will be what I would call anti-normal, meaning that the expansion away from their edges, both towards the past and future, will be negative, strictly negative, and there'll be a little gap in between them.
And why, like, so in like a lot of your papers, you're talking more about like bulk regions. So you only need this notion of this conformal shadow when you're trying to tie it to like null infinity as opposed to some screen or something else.
Yeah, so that's right. I'm telling you how to construct this fundamental complement of a region A, and that's going to be essentially the only time I will ever talk about infinity. Correct.
And you needed this though, even in your papers where you're not really always tied to infinity, or even in your AMAX story. Did you ever where did you need to have a tilde even if you were in flat?
So here's an example where my A doesn't even touch any infinity. So that's an input wedge in de Sitter space in this case. I could have done something similar here. It's just notice that it doesn't touch r equals 0 either. So this is really just the causal development of like an annulus or a shell, depending on how many dimensions you are in, right? Its entanglement wedge eventually is going to be like it's going to include its interior as well. It's going to go to r equals 0. But I still have to construct the sort of definitely out of reach region that is the analog of the boundary complement in ADS-CFT. And to construct that, I'm going to use infinity. So I look at the future of this and the past of this A on past and future infinity, and then I take the double complement, which gives me this this region A tilde.
So I mean, I guess the question is why you have to. I mean, it sounds interesting and physical to want to, but like you have all these like focus like SSA or your even and Emacs for a region. Like, is there something wrong with that in the flat context, or it's just that you want to do something extra?
Now, this is not in the flat. So notice these are all different asymptotic structures. This is something we have to always do. So there was, like away from ADS, the prescription that Geoff and I gave in our original paper on this topic was just not correct. And you would get, you would get wrong answers in certain cases here if you took that prescription. This one seems to avoid all those difficulties and still let us prove all the important results about wedges, entanglement wedges, which I'll get to next. Yeah.
What is the value of the expansions at the corner of A? Is there a restriction for you?
So because this is generated by causal horizons,
Yeah.
this will have negative expansion.
On both. That's
Same
it.
thing for A tilde. But for the same reason that came up in your question, this A is not actually bounded by causal horizons. This is a bit confusing. You have to think about beyond the symmetry structure that we sort of implicitly use here. You first construct that you still have to take the double complement. There's some light rays that sort of shoot above and below the causal horizons a little bit. It's not critical for this talk today that you understand this in real time. Yes?
I have a related question. So,
Yeah.
By the way, will you later give example where the gap is? Because it looks a little bit contradiction to the Hager duality of the flat space quantum field theory, for example. Like I know you are defining things geometrically, but
sorry. There's no contradiction here. This is just a completely different construction. There's also something we call A prime, which is the space-like complement to A. I defined that earlier.
Yeah.
And that's going to be exactly the thing you want it to be.
yeah.
Okay, and it's going to start at this edge. This is just a different thing. I need there to be some room between A and A tilde in general for the search for an entanglement wedge. It's going to live somewhere in between those two.
Okay.
Yeah. I see people are really following on. The questions are great, but maybe I need to also worry a little bit about time, especially since I've now just noticed this clock counts backwards, not forwards. Can I? It's an innocent mistake. All right, so I will not really go over the entire, I mean, this is a handful. I will point out that most of what's different from how you would define entanglement wedges in ADS-CFT is in what I've already told you. Okay, the rest is still fairly involved just because you have to deal with these conditional smooth max entropies and min entropies for the min entanglement wedge, which require a more sophisticated way of stating, roughly speaking, the maximin prescription that Aaron Wall gave. It's more sophisticated just because you cannot split a conditional max or min entropy into a simple difference of two generalized or two entropies, which means that there's not a single quantity you can somehow maximize or minimize anymore. And so this requires you to define the max entanglement wedge essentially as a union of a bunch of anti-normal wedges that satisfy the homology condition. They have to contain A, and they have to not overlap, or not even, they have to be completely space-like related to the fundamental complement of A. And Well, we make an exception for where those wedges have the same edge as A itself. So for example, if A is like a ball in Minkowski space, then the entanglement wedge of A is itself. That's not anti-normal, it's very much normal surface. And that has to be okay, otherwise we get the empty set. Yeah, so these are, this is a key change, and this exception here is a key change, and the rest.
And for the min wedge, you already had that exception.
So, oh, you mean change relative to my paper with Geoff? This is the change for the this is the change for the max wedge. Here we had previously required that it has the same edge on the conformal boundary as the input wedge.
Sorry, when the metric fluctuates, do you need to adapt the definition, or does it matter?
So this is a big question, because the question is, what do I really mean by semi-classical gravity? And it seems like this vague thing that we don't really, what exactly does that mean? I think to make it precise, you need to take a limit where you have a large n number of fields at fixed g Newton times that n. And in that setting, one would assert that all these things, the quantum focusing conjecture, the generalized second law, and so on, are exact statements. And in places where that can be analyzed, like for example, if you have a brane world at infinite n, or in this limit, Arvind Shahbazi-Moghadam has actually done that and has shown that the quantum focusing conjecture holds as an exact statement. So that's the best I can answer your question. All right. Good. The min entanglement wedge, let's not spend too much time on the min entanglement wedge. It's an intersection of normal wedges, and you use the min entropy instead. The real problem with our prescription, by the way, was the min entanglement wedge, not the max one.
Is it weird, like why does it suddenly need the boundary? Because like in the original paper, it's like you could choose to put the region near the conformal boundary, and then you're getting things that are related to the entanglement wedges.
Yeah, you can still do that.
But you still need the conformal boundary to even define these regions right now, right? Or
It's just part of the prescription. Yeah.
no, but I'm saying before it.
You can still choose arbitrary regions. That hasn't changed.
Sure.
So that's the important thing. You can choose as your input any bulk region. It's just that it turns out that you need a rigorous definition of the analog of the complement boundary region, and that's where infinity comes into play.
It seems interesting that it does come in, right? Because in the previous papers, I might have felt like, oh, I can just do things in the bulk, and now it's like I need infinite. Yeah.
Well, I mean, you can always do everything in the bulk, right? Infinity is a convenient mathematical shortcut for something where you could take some limits and just do everything in the bulk. But yeah, so the prescription does, so why do I think this is right? Like in ADCFT, of course, the reason that people believe in Ryota Kayanagi has to do with the fact that, for example, you can just compute the entropy of certain CFT subregions directly. Not all of them, but a lot of them. And you can check that you get the same answer, and there's like a ton of highly non-trivial checks like that. So how do I know that we're not totally deluding ourselves here in claiming that this is an appropriate analog? And here are some examples of results which have sort of no right to be true. So first of all, I can't promise that we're not deluding ourselves. It's a conjecture. But there are several results that have no right to be true if these things are not entanglement wedges. One is that you have versions of nesting and no cloning. In other words, if, for example, if A and B satisfy suitable independence conditions, roughly that they're outside each other's entanglement wedges, then you can't use them to sort of recover the same information. I mean, if you think of an entanglement wedge as sort of a thing where you could have put an operator, there exists an operator in the algebra of the input region that like pulls out some information from this deeper entanglement wedge, it would be a problem if the entanglement wedges of A and B were able to overlap. This is somewhat related to complementarity in ADS-CFT. There's a much more difficult to prove multi-page thing where you can prove that entanglement wedges satisfy strong subadditivity, and they do this even at the sort of refined level of these min and max conditional entropies, these things reduce to the statement of strong subadditivity of the generalized von Neumann entropy. The reason that that's not obvious is that there are area terms in these expressions. This is not manifestly from the start an entropy. Yes?
To follow up to Sabrina's question, so is the implication that you believe something like this construction could be defined even in the absence of a conformal boundary, although maybe you don't?
No, it is always defined. It doesn't matter at all if there is a conformal boundary. I never said there had to be one. Yeah, sorry, this was maybe not clear. This is whatever scry is. If there's no conformal infinity, then this is just the empty set, and you just do exactly the same thing either way. So there's no assumption here that my spacetime has a conformal boundary. It's just that whatever the conformal structure looks like will matter for the construction of A tilde. Yeah, I'm so glad you asked that. Sorry for, yeah.
Is the black hole singularity part of the?
No, so I should have been very careful, and I was hoping I would be, and clearly wasn't. But yeah, I always mean conformal infinity when I say boundary. That's important for this to give sensible answers. And it's, roughly speaking, you can think of this as like a sort of causal wedge of the relevant, of the part of the boundary that's not in the conformal shadow of the input region. In the ADS case, it's exactly what we would normally call the causal wedge. This is a region that we can completely control from this side, right? And that's why it's very sensible that we exclude it from, overlapping with the entanglement wedge of A from the beginning. Right? It would just not make any sense to be able to reconstruct anything that's in here, because it depends on data on this part of infinity that we can completely control.
Do you have any interesting statements about like the entropy of like the boundary region for that shadow and the one of the bulk region A or something?
Let's take that offline because I'm running way behind time. All right. Let's see. This is a student at Berkeley, Elisa Tabor. With Geoff, we had proved this at the level of the generalized entropy, the von Neumann generalized entropy, and we were able to show that this holds even at the level of these min and max entropies. And one more piece of evidence before I go to like more examples and specifically asymptotically flat space is, and I really want to give a lot of credit to my student Sami Kaya for this, because first of all, he was the one who thought of this originally. I never thought there was any chance of having an analog of entanglement wedge complementarity in the bulk. And it's simply because, for example, if I give you a shell here in this room and I ask what its entanglement wedge is, well, it's going to be the full ball, like it fills in the interior. That's pretty obvious, right? But if we look at the complement of that shell in, I don't know, Minkowski space, well, that's everything but the shell. Its entanglement wedge is the entire space-time, and it includes that ball. It overlaps with that ball. It's not complementary to it. So to me, this was like, okay, too bad. You can't get everything. I mean, we moved into a different sort of territory, and that's just not going to, I'd given up on that. It's not going to come back. It seemed pretty obviously not ever true. But Sami pointed out, this was originally sort of in this ADS kind of setting. Just compute the entanglement wedge of the complementary boundary region of whatever was not touched by the input wedge A. Now, of course, at that point, we'd have the same problem I just described. You'd get an overlap. But all you need to do is exclude from the space-time the input wedge A. Restrict, in other words, to A prime, to its space-like complement. And even then, so if this is the entanglement wedge of A, now if you have a boundary out there and you look for its entanglement wedge, if you've excluded just the green portion, you will still stop here. You will start filling in. This will be in the entanglement wedge of this infinitely far away boundary. But you're going to stop here because otherwise this, you get a non-minimal surface as your boundary, and it doesn't like that. And there's lots of examples like that. I'll show you more examples where this just works. I was initially I didn't believe it, but it just works. And this is actually what led us to this, to realize that we hadn't gotten our asymptotic boundary conditions correct in spacetimes other than ADS, and led us to do all the stuff I've now told you about, because we weren't, it wasn't working in the beginning in sort of general settings, but that had nothing to do with this idea. It had to do with the fact that we hadn't gotten those conditions right. So I just want to, before going to the examples, my take is, okay, there's some evidence that these entanglement wedges in the bulk obey, several non-trivial properties that they have no right to obey unless they represent in some sense of an algebra in the fundamental theory. I don't know how to make this much more precise, but I want to give you one sort of thing to cling on to. If my input region A was the exterior of a very large sphere in ADS, then, let's say if this is in a vacuum, then it's entanglement wedges, of course, the whole space-time. We could note that quasi-local bulk operators that are within the semi-classical regime in the input region A are dual in a very simple way to local CFT operators nearby on the boundary. Okay. Where things start to go different in bulk and boundary is if we ask about the entire algebra generated by these operators. On the boundary, that's going to be the whole CFT algebra. In the bulk, well, at the algebraic level, it's exactly the same thing. It's an algebra. But in the bulk, most of those operators have no interpretation as a semi-classical operator in this asymptotic shell A. And so my take for the time being on what these entanglement wedges mean is that roughly there is some algebra that's generated by the semi-classical operators in the input region that accesses, that in some sense corresponds to what operators are in the entanglement wedge that's associated to that input region. And please don't push me on that because I really don't know how to be more precise than that. Okay, so here's some examples which I won't spend much time on because I don't have any, that are mostly designed to sort of recover what we know about how entanglement wedges work in ADS. One can consider reflecting boundary conditions. One can consider arbitrary boundary conditions, in which case you have to sort of cut off the space-time because you don't know what you're going to be sending in or what's coming out over here. And in both cases, things work. Here are two fun examples where we have an ADS setting, but yet there is no analog of these examples in the original sort of ADS CFT, entanglement wedge story. What I've done here is I've taken an asymptotic region in the bulk that looks like this, and then when you looked at the sort of space-time diagram, you would notice that I've wiggled the edge of this region so as to give it very, very little area. These are sort of zero distance type null pieces. In that case, you find that the entanglement wedge of this region A is in fact not the usual, the naive, ADS CFT entanglement wedge, which would go out to this blue line. At least not the max entanglement wedge. The min entanglement wedge is this thing. Okay. So already at the classical level, I didn't need to talk about generalized entropy, let alone min and max entropies. This has no, this didn't exist before. At the classical level, we already have a distinction between min and max entropies in this case. Same here. This is an input region A. I've only shown a Cauchy slice of it here in green, which extends into a two-sided black hole. The max entanglement wedge is again A, and the min entanglement wedge, if you check according to the prescriptions that we gave, it goes out to this horizon here. It has to be a normal surface, so it has to go out to there. And it's fun to check the complementarity story. These were the first examples I checked when Sami claimed to me that there's this complementarity. Like if you exclude, if you restrict to A prime, for example, then the entanglement wedge of this right boundary is indeed precisely, the max entanglement wedge ends here and doesn't go down to the bifurcation surface. So it's a nice thing to check. Before going to asymptotically flat space, let me just mention some de Sitter examples. So you've already seen this one when I discussed how to construct the fundamental complement A tilde. And when we now ask, having done that, when we now ask what is the entanglement wedge of A, well, it fills in this hole in the shell. It's in this case not particularly important. It seems that A tilde has been excluded, but in fact it is important, because usually when we discuss closed universes, we get to include the entire closed universe for free, because then we have zero area, so that's favorable as an extremal surface. It's more minimal than still being left with this edge area here. But because we've excluded A tilde, we don't get to do that. So that's a new phenomenon. On the other hand, for a big enough input wedge, whose conformal shadow is all of scry as it is here, then yes, then we're going to get the entanglement wedge to be the entire spacetime. There are also weird, funny wedges like this, which sort of cling on to scry plus, let's say. And in that case, the entanglement wedge is just the wedge itself. Here's a funny example in Schwarzschild de Sitter. We pick this as our input wedge, and the entanglement wedge actually picks up a little piece of scry minus in this example. The fat part is supposed to be the Schwarzschild singularity, and this is the actual proper infinity. All right. In the remaining 5 minutes, I will tell you all about flat space. So here are some straightforward examples. This is an annulus or shell as an input region. I've already told you it fills in the shell. It's going to be useful just for comparison with the coming slides to look at what exactly the conformal shadow of A looks like. The conformal shadow is this brown part here. I've represented scry plus and scry minus. I've sort of fanned out the generators a little bit so that you can see it better. This is spatial infinity. Okay. Now, if A is a Rindler wedge, it gets a little bit more interesting. You've already seen the construction of the conformal complement. If it's really in flat space exactly, like no perturbations, then A will agree with E of A. But if there's a sort of generic situation where you have a little bit of matter around, then both A and A tilde will be antinormal from their own perspectives, and there'll be a little gap in between, and the entanglement wedge is going to find a nice place somewhere in that gap where there's an extremal surface. Okay. Now we can start breaking some symmetries. For example, we can put a little notch into our Rindler wedge. Let's say in exactly Minkowski space, so we can just focus on that one thing. Well, then the entanglement wedge will fill in the notch. Okay, that's pretty obvious. I mean, at least it's what you would intuitively want it to do. But originally we had some problems without this careful treatment of A tilde that the entanglement wedge would sort of want to run away. That's actually how this, yeah. Now, what's funny is if the Rindler wedge gets a bump added to it. That's more interesting. The bump will make the conformal shadow bigger. See that the brown region, which is the conformal shadow of A, is coming down a little bit here. There's less left of this one geodesic that's going to be in its complement. That's just because the bump, the light rays coming from here have a head start, and that's the only thing that matters. All these other loser light rays coming from the rest of the edge are just not helping. This is the pioneer. And so in that case, you do get a big gap, potentially, between A and A tilde. And what the entanglement wedge will want to do is fill that back into a Rindler wedge. So it really fills in all of this stuff. I find it helpful to think of this as like drawing an extremal surface to some IR-regulated version of this Rindler wedge. And it's going to go a little bit diagonal, but then as you take the IR cutoff away, it's going to expand out to a proper Rindler wedge. Let me finish and then take questions, just so I don't get the army to march me out. Unions and intersections of Rindler wedges are interesting as soon as you have even a little bit more than one Rindler wedge. So it wasn't important that I take the union of a Rindler wedge with a 90-degree rotated Rindler wedge. Even if it was just 1 degree rotated, the entanglement wedge would immediately become the whole spacetime.
So,
sorry?
I think I was worried because
So now spatial affinity doesn't come into it, right? Because the past and future of A will never reach it, no matter what I do. Yeah. So in this case, the conformal shadow is just everything. And so the complement is empty, and I get the whole space-time. On the other hand, if I intersect two Rindler wedges, then, and I don't put any notches in them or something, then E of A is A. Okay. And I get, for the complement of the conformal shadow, I will now get sort of an arc or a solid angle's worth of half geodetics on scry. Okay, I won't go into more examples because we are predictably out of time. And I'll leave you with the key takeaway message and take more questions if they let me. Thank you.